So you want to estimate the mean IQ of the general population based on a randomly selected sample of people. You get 16 people to take an IQ test, and their scores are shown in the table below. So historical data shows that the standard deviation of IQ in the population is 10, and we need to use this information to estimate a 95% confidence interval for average IQ. Alright, so I'm going to start by drawing us a diagram of all of the information we're provided in the question. So I'm going to say that this here is my population of people. Now the mean for that population is what I'm trying to figure out, so I'm going to leave that as a question mark. However, it tells us that we have a standard deviation for that population, which is equal to 10, so we can pop that in. So in order to figure out an estimate for this population mean, we're going to draw out a sample of people, and we know that our sample here has 16 in it. So that's what n is going to be equal to. And we're provided with all of the data. However, we've got this little note down here that tells us that the mean of the sample, so that's x bar, is equal to 106.63. So rather than us putting this into Excel or a calculator to figure it out, we've just been provided it up front. Alright, so what we're looking for here is the 95% confidence interval. So I'm going to put that as CI, and it's for our population mean. Now we have two kind of options for how we go about writing the equation. One option is to write it in terms of Z, or the Z distribution. The other is to write it in terms of T, for the T distribution. Now what defines how we make that choice is this standard deviation parameter for the population. So if you're provided that value, then it tells you should be using the Z version of the equation, and if we were not given the standard deviation for the population, then we would use the T version. So we're going to use Z, and that means that the equation looks like this. Okay, so x bar, which is our sample mean, and then we're taking away for the lower limit here a Z score, and this is going to come from the 95% that we've been given. And this here is our standard deviation for x bar, the sample mean variable. So the upper limit here, it's the very same form of the equation, except we have a positive. Alright, so one kind of important assumption that we're going to need to make in order to perform these calculations is that our x bar variable, which is our sample mean, we're going to have to assume it's normally distributed. Now this is something that isn't quite so implied, I suppose. That's because we have a rule of thumb where if the n value, or the number in your sample, is less than 30, then it's not necessarily normally distributed when you look at sample mean. However, if n is greater than 30, then you can kind of make this assumption quite easily. It's almost implied that this is the case. Okay, so we're going to need to make this assumption, which possibly is a bit questionable, and we don't really have any means to kind of check it at this point. But what it means is, since we are making this assumption, we're now going to be able to directly calculate what the standard deviation of our sample mean actually is. And we have our equation where it's equal to sigma for the population divided by the square root of n. So we can substitute in, this is 10, and we said n was equal to 16. So this becomes 10 on 4, or the same as 2.5. Alright, so let's draw ourselves a little diagram of this normal distribution of x bar. It's going to look something like this. We've just figured out the standard deviation, so I'll pop that out here. And the mean of our x bar, for the purpose of estimating this confidence interval, is going to be the mean of whatever we had for the sample. So we've got 106.63. So in order to get out our Z value, we said that it was related to this 95% thing. So we're going to end up with a lower bound on our x bar and an upper bound on our x bar, which is essentially going to be the answer here for the lower and upper bound of our confidence interval. And we're assuming that we have 95% confidence. So that's going to mean that this region in here, between the lower and the upper bound, has to have an area of 0.95. Alright, that then means that these bottom and top portions here have the remainder. So if the total area under the curve is equal to 1, and we've already used up 0.95, that means that in here it's going to have to be 0.025 or 2.5%, and 0.025 here. Alright, sometimes you might see people say that this is equal to alpha on 2. That's because alpha is going to be the difference between 100% and 95%. So in this case, 5. So 5 divided by 2 gives you 2.5% or 0.025 in decimal form. Alright, so this is currently in terms of x bar. In order to look this up in tables though, we're going to need to flip it into z, and of course z is what's going to end up in our equation up here as well. So when we convert from x bar into z, we know that the mean here ends up going to 0, and we need to find where this boundary actually lies. So if we take note that this upper part here has an area of 0.025%, what I'm going to do is shift over here and look at my inverse table. So we can see that we have an area in here which is called our right-hand tail, and we said that this in our case was equal to the 0.025. So if we look down here, 0.025 sits here. So that means that it equates to a z-score of 1.96. So if we go back and mark that on our diagram, that means here on the z scale is the same as 1.96. Okay, and this is going to be the negative version, so negative 1.96. So this is now our z value that just needs to get popped up into our equation. I might come over here. So our confidence interval is equal to x bar, which we said was this 106.63, minus our z value, which is the 1.96, multiplied by our standard deviation, which is 2.5. So that's the lower limit. The upper limit is this just with a plus in here. So if you type this into a calculator, you end up with the lower part becoming 101.73 and the upper part becoming 111.54. If we look at it back on our diagram over here, this part, that's that 101.73, and this one here is the 111.54. Alright, so the last thing I wanted to say was how this is kind of interpreted. So what we can say is that we are 95% confident, since that was our confidence interval that we were given. So we're 95% confident that the true population mean, which is mu, is between our lower and upper limits. So 101.73 and 111.54. Alright, so that's pretty much all there is in terms of this video. That would be my final answer for what we were asked. So I will see you in another video.